In a gas turbine unit, the gases flow through the turbine at the rate of 15 kg per second and the power developed by the turbine is 12,000 kilowatt. So here it is given the mass flow rate 15 kg per second and power or work done by the time, which is given W equal to 12,000 kilowatt or kilojoule per second. The enthalpy of gases at inlet and outlet are 1260 kilojoule per kg and 400 kilojoule per kg respectively. So H1 and H2 given, H1 equal to the 1260, H2 equal to the 400. The velocity of gases at inlet and outlet are 50 meter per second and 110 meter per second. So V1 equal to the 50 and V2 equal to the 110. Then calculate the rate at which heat is rejected from the turbine. So I have to determine the heat transfer rate. So we know the steady flow energy equation, and in the data it is mentioned that gas turbine unit, and also in the data it is given M value is given and H1 and H2 value is given, V1 and V2 values also given, and work done also given. But it is not given the any data respected to the elevations. We know that in the turbine unit the differences between the elevations is the negligible. So I have to consider the potential energy is negligible. So and we know that M1 equal to the M2 equal to the M. Then we have to substitute all these values in the above steady flow energy equation. Then 15 into 1260 plus 50 square divided by 2000 plus Q equal to 15 into 400 plus 110 square divided by 2000 plus 12,000. So if you solve this equation, we will get the heat transfer rate Q equal to the minus 828 kilojoule per second. So let's see, the next question is the area of the inlet pipe when specific volume of gases at inlet is 0.45 meter cube per second. So we have to determine the inlet area A1, we have to determine, and given the specific volume of the gases at inlet. So nu1 equal to 0.45 meter cube per kg. And we know that mass flow rate at inlet M1 equal to A1 V1 divided by nu1. So we know the mass flow rate M1 equal to M2 equal to M, and velocity at inlet V1 value we know, nu1 also given in the data. So substitute all these values, we will get the A1 value is the 0.135 meter square. Let's see the second problem. At the inlet to a certain nozzle, the enthalpy of the fluid is 3025 kilojoule per kg and the velocity is 60 meter per second. So here it is given the inlet enthalpy, that is the H1 3025 kilojoule per kg, and inlet velocity is given 60 meter per second. At the exit of the nozzle, the enthalpy is 2790 kilojoule per kg. So H2 value also given, that is the 2790. Nozzle is horizontal, so Z1 minus Z2 equal to the 0. There is a heat loss of 100 kilojoule per kg from it. So heat loss, so that too it is given in kilojoule per kg. So units are very important while solving the steady flow energy equation. So previously heat transfer rate is given, that is the kilojoule per second, but here heat loss is given the kilojoule per kg. Let's consider small q equal to the minus 100 because it is the lossing. So minus 100 kilojoule per kg. So remember unit. Calculate the velocity of fluid at nozzle exit. So have to determine the V2. Also find the mass flow rate of the fluid if the inlet area is 0.1 meter square and specific volume at inlet is 0.19 meter cube per kg. So have to determine the mass flow rate, and given the inlet area A1 equal to 0.1 meter square, and specific volume at inlet also given, that is nu1 equal to 0.19 meter cube per kg. So first we have to determine the velocity of fluid at nozzle exit. So how to determine the V2 value. So we know the steady flow energy equation, and here Z1 minus Z2 is negligible, that is the 0. Then there is no potential energy, and moreover we know that, so in the nozzles there is the no shaft work output, so work done also have to consider the 0. And equation will become the m into h1 plus v1 square by 2 divided by 2000 plus q equal to m into h2 plus v2 square divided by 2000. So here remember, so in the steady flow energy equation, q is the heat transfer rate, that is the kilojoule per kg. But in the data it is given the kilojoule per kg. So how we will get kilojoule per kg mean q divided by mass flow rate. So entire the equation we have to divide it with the mass flow rate with the m, and here m will get cancelled, and q by m here, and here also m will get the cancel. Then this equation will become the h1 plus v1 square by v1 square divided by 2000 plus q equal to the h2 plus v2 square divided by 2000. So we know the all the values. So substitute h1 v1 h2 v2 and q also we know. So equation will become the h1 value 3025 plus v1 value 60. So that is the 60 square divided by 2000. So q equal to the 100 kilojoule per kg. So heat loss, so that's why it is the minus. So q equal to the minus 100, and h2 is the 2790. Then we have to determine the v2. So if you solve this equation, we will get the v2 value is 523.07 meter per second. So and also we have to determine the mass flow rate of the fluid. So we know mass flow rate equation m equal to a1 v1 divided by nu1. So in the data a1 is given and v1 is given and nu1 also given. Substitute all the data, we will get mass flow rate is the 31.58 kg per second. Let's see the another problem. Air flows steadily through a rotary compressor. At entry, the air is 20 degrees Celsius and 101 kilopascal. So initial temperature and initial pressure is given. So T1 equal to 20 degrees Celsius and P1 equal to 101 kilopascal. At the exit, the same air is at 200 degrees Celsius and 600 kilopascal. So it is given the T2 final temperature 200 degrees Celsius and P2, so final pressure 600 kilopascal. Assuming the flow to be adiabatic, so it is the adiabatic flow, so then there is a no heat transfer. Then evaluate the work done per unit mass of air if the velocities at inlet and exit are negligible. So here you have to determine the work done per unit mass, that is the kilojoule per kg. So have to determine, so work done W equal to kilojoule per kg, and inlet and outlet velocities are negligible, so V1 and V2 equal to the 0. So we know the steady flow energy equation. So here there is the no potential energy and the kinetic energy, and also adiabatic flow, so there is a no heat transfer. Then this steady flow energy equation will become the m1h1 equal to m2h2 plus W. So here W in the steady flow energy equation kilojoule per second, but here we have to determine the kilojoule per kg. Then we have to divide it with the mass flow rate m. So here m will get cancelled. So here W by M. Let's consider the small w. So then this steady flow energy equation will become the H1 equal to the H2 plus W. And we know in adiabatic flow, so enthalpy is the change in enthalpy is the H2 minus H1 equal to Cp into T2 minus T1. So we know the Cp value. Cp equal to the gamma divided by gamma minus 1. Gamma value for the air is the 1.4 and R value we know. So that is the 287. Then substitute Cp value we will get 1004.5 joule per kg Kelvin. So I have to substitute in the H2 minus H1. Then H2 minus H1 will become the Cp into T2 minus T1, that is the 1004.5 into T2. So final temperature 200 degrees Celsius, it is converted into Kelvin, then it is the 473. T1 20 degrees Celsius convert into the Kelvins, that is the 273 plus 20, that is the 293. Then solve this one. H2 minus H1 value is the 180.81 kilojoule per kg. So here work done is the H1 minus H2, then work done will become the minus 180.81 kilojoule per kg. Next we determine the what would be the increase in work input if the velocities at inlet and exit are 50 meter per second and 110 meter per second respectively. So given the V1 and V2 values, then we have to determine the work done. So we know steady flow energy equation. Here only potential energy and heat transfer rate only negligible. Then this steady flow energy equation will become the M into H1 plus V1 square divided by 2000 equal to M into H2 plus V2 square divided by 2000 plus W. So here W is the kilojoule per second, but we have to determine the kilojoule per kg. So in this one we have to divided with the M value, then here M will get cancelled and here work done will become the, so work done per mass flow rate, that is the kilojoule per kg. So then equation will become the H1 plus V1 square divided by 2000 equal to H2 plus V2 square divided by 2000 plus W. Then W equal to H2 minus H1 plus V2 square divided by 2000 minus V1 square divided by 2000. So we know H2 minus H1 we know, V2 value we know and V1 value we know. Substitute all these values, we will get the work done is the 185.61 kilojoule per kg. So this is the solution and thank you.